Hi, everyone. Uh, Good afternoon. So first, I want to say that I'm sorry for not being physically in the summer school, but I'm following the event and by internet, and I believe you all are having good times in Wageningen. So let's start. I will start my presentation. So my name is Leandro Parente. I'm a postdoc researcher at OpenGeoHub Foundation. And today I will talk about Google Earth Engine and how we can efficiently use it in R. And my presentation, my talk is organized in three parts. So the first part uh, is about the platform, the Google Earth Engine, an introduction about this outstanding platform and how we can integrate R with it. And in the second part, I will do a code demonstration in the RStudio. So we will run a land cover classification for a Landsat scene located in the Amazon forest. And in the last part, I will summarize some concluding remarks. So first, what is Google Earth Engine? For me, Google Earth Engine is a free cloud computing platform capable to analyze on-the-fly science data in a planetary scale. So it's important to say that free doesn't mean free software. Here, Google Earth Engine is a business solution developed by Google, but anyone can sign up and start using the platform, run your own analysis and upload your own data in the Google infrastructure and take advantage to that in your own workflow. And other important aspect is this platform promotes on-the-fly planetary analysis. So it's a great functionality because we can easily access all the data from, for example, Landsat or Sentinel in any part of the world, and we can visualize the result in some seconds. So it's a great functionality too. So basically, anyone that work with Earth observation data knows that we need to download this data from several Earth observation from several providers to our own server, to our own workstation or own server hosted in a cloud platform. But we need to download the data to start run our customized algorithms and analysis. With Google Earth Engine, we need to think in an opposite way. So basically, we upload the code through the Google Earth Engine, and we run some specific analysis in that infrastructure, that cloud infrastructure, to process several Earth observation data organized in one place. So we can scale up any type of analysis, for example, through the whole world using the same code. So it's an important aspect in this type of paradigm named moving code. So what are the public available datasets in Google Earth Engine? So we have all the Landsat archive since '85. We have Sentinel 1, 2, and 3. We have SRTM, ALOS, Open Land Map, soil data, and several climate datasets. And we can consult, we can access and search in this catalog through this link. So you can easily discover if some specific dataset is available in there. And if not, you can upload it by your own, or you can ask to Google team to upload and to insert it in the platform. And about the architecture. So basically, Google Earth Engine is a cloud computing solution. So we need to interact with the platform by client libraries. So there are two official client libraries developed in JavaScript and in Python. And using this library, we construct descriptor. We construct like a representation, an object representation of our own analysis, and we submit it to the cloud platform to process and to run in the Google infrastructure. So basically, we receive the output of this analysis by two ways, by on the fly, so we can analyze and visualize the result in a web map solution, or we can export it to a batch computation directly to Google Drive or to Google Cloud storage. So here we can see an example of this on-the-fly analysis. So this is the annual median for NDVI, considering all Landsat 8 observation for 99, for 20 in 19, 2019, sorry. And this data is a surface reflectance data. So basically, if you click in this code, you will access the JavaScript code in the code editor, and you can visualize the output, the output of this analysis in an on-the-fly way directly in your browser. And basically, what is happening here? So in this analysis, I removed all the cloud and cloud shadow pixels. So each pixel that has some type of contamination, I removed it from all the images available in Lens in 2019. And I got this time series with a lot of gaps. And after that, I apply some type of temporal reduction by median. So basically, in this specific example, we have 0.4 as output result for one specific pixel. But what I implemented here is a specific way to reduce all the images obtained for a specific year to one image. So I reduce the one image collection to only one output. So we can apply several types of reduction. So this is a very common operation in the platform, and you can access it directly by this link if you have the access to Google Earth Engine, and you can check it for any part of the planet, as I calculated it for the whole world. And considering that, a good way to work with Earth Engine, we are doing it in OpenGeoHub. So a good way is use the Google Earth Engine in part of your workflow. So here, for example, I can upload this code to generate a median annual NDVI image for the specific year and export only this output. So I process all the Landsat archive for a specific year and generate only one output to Google Drive or to Google Cloud Storage and download this result to run other types of analysis in our own servers. So a good example of that is it. So here we can see all the NDVI data for the whole world obtained by AVHRR for the year of 19 and 91. So this is purely Earth Engine. If you click in this link, you will have access to the code that generates this GIF and this animation. And what we did at OpenGeoHub, we downloaded all the monthly NDVI data for the whole world. We downloaded it from VHRR data and from MODIS data. And we run locally a smooth and a gap view approach using this package, this green-brown package. So this is a good example of how we can actually run and incorporate Google Earth Engine in one workflow, because the monthly analysis for this whole period was implemented in Google Earth Engine, and we only downloaded all the monthly NDVI data for several years. And about R, we need to know about it because Google Earth Engine only provides JavaScript and Python as official client libraries. So to integrate the platform with R, we could use this package. In the code demonstration, we will use this package, the RGAA. It's an official Earth Engine API, but a great piece of software. And what this package implements is integration between the Python API, the official Python API for Google Earth Engine, through Reticulate. And with this package, we can access on-the-fly computation in the RStudio, and we can export the output of our own analysis in to the Google Drive and to Google Cloud Storage, and integrate it with the Aerospatial ecosystem. So what you need to know about this type of integration. So first, you need to sign up for Google Earth Engine. It's free. You just need to click in this link and fill the form. After that, you need to install the RGAA package by a virtual env or a Docker image. There are two options to do that. After, you need to set up and authenticate in the Google Earth Engine, in Google Drive and Google Cloud Storage. Google Cloud Storage and Google Drive is optional. And I suggest to you read the best practice, because in this link you will find a good material to understand the difference between the Google Earth Engine and the Air environmental. So there are some difference that you need to know before start coding. And a good starting point is these Air examples. So here you will find several examples that was based in an official user guide and were rewritten in the R. And one important tip is that the official Google Earth Engine is only available in JavaScript. So to know the name of the methods, the name of the parameters, you need to access the code editor and check in the JavaScript, but you have access of all these methods and all the parameters in R and Python. So let's start our code demo. So first, we need to know what we will do. We will run a land cover classification for one Landsat scene in the Amazon forest. We will work with predefined samples that I collected for that area. We will use these samples as an uploaded asset in the Earth Engine. After, we will run a temporal reduction, overlay samples, and we will export the result of the overlay. So the pixel value for each sample that was calculated over Landsat data to Google Drive. And after that, we will run a random forest tuning approach using MLR3. I won't talk about too much about MLR3 because I don't have time enough, but it's a great piece of software too, and you need to check it. I suggest you to check in the website, in the official website. And after that, we will run a classification for the whole area, considering all the Landsat scene, and export the classification result. So you will find the code here. So if you click in this link, you will find the presentation, the samples, and the code that I will run in R. So I put here other one extra file with some type of analysis and some suggestion to configure the environment in the RStudio. And if you access, I will access only quickly the code editor here to show that we will use this asset. So I uploaded the CSV file to Google Earth Engine. So you can upload the GLT shapefiles, CSV files. I uploaded my CSV file to Google Earth Engine, and anyone can read it because I share this asset with a public. So this asset is public. So we will access the samples that are stored in the inside of Google Earth Engine in RStudio. So first, I will, starting with these helper functions, I will talk about them in the next minutes.
Leandro, can you please increase a bit the font size in RStudio under Tools, Global Options?
All right.
Under Appearance. Yeah, and then you edit the font size. Yeah, put like 18 or something like this. Yeah. They want also the theme to change into white. It's easier to read. Yeah, it's difficult to read on this screen. Yeah.
All
yeah,
right.
Sorry about that.
I will change here.
That's the yeah, something like this. Yeah, Chrome is fine. Okay, great, much better. Thank you.
All right. So I will starting with these helper functions that I will talk about in the next minutes. But basically, I wrote these functions to help in this code demonstration. And I will load the RGAA package. You need to configure it in your own machine. There are information, you will find this information in the official website, but in the extra, you will find the dependencies that I installed and what are the functions that you need to run to set up, for example, the authentication. You just need to run it one time. And to start the code demonstration, first we need to initialize the connection with Google Earth Engine. As I said, Google Earth Engine is a cloud computing platform, so we need to establish a first connection with the platform to starting use it in R. And I will access my samples that I uploaded in the Google Earth Engine through this function. So basically, feature recollection is a representation of vector data in the Google Earth Engine. And this is the ID, the unique location of some data set that is provided in the Google Earth Engine. And we need to, the first thing we will run is what is the number of the samples that we have here. So it's an important part because if you run only this code here, sample size, you will get only this Earth Engine object number. So basically here, you don't have a result of the output, the analysis, this method, because in this part of the code, we only have a description of some type of analysis. So basically, we need to send this description to the platform to run in the Google Cloud infrastructure, and after that, download or get the result. You only will have the result if you call get info. So basically, if you want to access any type of result, considering this method, considering these functions, you need to call the get info to get the real result of analysis, forcing the API to access the Google Cloud, the Google Earth Engine, and get the result from the cloud. So this is one type. We will have the access of the data through a viewer. That is the other type. So we will access the samples, and we will see it in a web map. I will show in the next minutes. So what are the sample attributes? So basically here, we will see that we have an ID and a property named land cover, containing the values of land cover for the sample. And in this toy sample, we have a forest. We have samples for forest, pastureland, crops, others, and water. So basically, I will create a list with one color for each of this class, and I will use this function that I implemented to plot all the samples, separate them by colors. So basically here, we are seeing all the samples organized by layers, by class, and the number of samples that we have in the each class. And we are seeing, so this is stored in Google Earth Engine, and now we are seeing the result in the RStudio. So it's some type of the on-the-fly visualization. Basically, this function is responsible to split the samples and apply the color using the parameters of Google Earth Engine. What we will do now is calculate and visualize the sample extent. So you can see that I'm reduce all the geometries of the samples, and I'm calculating the bounds, so the extent of that sample. And I will put this result, this output, in a layer, and I will put the layer in a list of layers. And if I send to my function this layers object, it will plot the samples and the what we have in the list. So basically, we are seeing here the extent of our samples. So this is a bounding box, and it's important because we will use it to refine, to specify what is the spatial extent for our analysis. So basically, to run this analysis, we will reduce all the images of Landsat data, considering surface reflectance product, obtained for the whole year of 2019. I will filter by these three, by these all spectral bands, and I will pass this extent. And this is an important parameter because this is a mathematical representation of our valid pixels. So Earth Engine will use it to remove the cloud and cloud shadow pixels using the Landsat quality band assurance. So to understand these values, you should access this official documentation by USGIS to understand what are the values that are maintained here. And I will run a reducer. So we can access, we have several reducers like standard deviation, median, but in this case, I'm running the percentile 25, the percentile 50, and the percentile 25. So basically, I will, so I need to create this. So basically here, we only have the descriptor. We don't have all the Landsat data here in my notebook, but we can visualize it in the viewer when we put it on the map. So for example, if I call this function band names and a get info, so I force it now, the API to access the real band names in the Google Earth Engine and retrieve to me in the object representation here in R. So by default, Google Earth Engine don't provide any type of enhanced, so automatic visualization for Landsat data. And I create this function to basically calculate the minimum and the maximum values for each of specified bands. So it's only a function to define the visualization parameters that will be used in the map. So now we will see the annual median for all the spectral bands in our interesting area. So we can check, for example, if the forest samples are in the right place and things like that. So we have all these.
Leandro, question. So now, so you calculated these satellite bands, you calculated in Google Earth Engine, right? And then you now load it, you display it in R. Is there any like a temporary object that you download from Google Earth Engine to your machine? I mean, or is it just really loads it in the memory? How does it work?
No, it's work really on the fly. Here, I only have access to a tile server that is provided by Google Earth Engine. So all the analyses were processed in Google Earth Engine. In here, I only have a visualization of that, for example, in PNG, that is available in the web map. So,
okay, so you don't have the actual data. You don't get the data locally. You just got the PNGs from the. Okay.
Yes.
Okay.
But it's important thing because, for example, I can check it and I can see that that image has a lot of clouds because for example, my valid expression, my mathematical expression actually didn't remove the cloud. So it's good to have this type of representation before to download the data.
Okay, continue, please.
So what we will do now, so I calculated it for all these Landsat bands. So it's 21 bands. And now I will export the data. So what this function implements, this function extracts the Landsat percentile values for each sample, export it as a CSV file to Google Drive, download it from Google Drive, and load it in R. So basically, here I send to the function the samples and my image. This image is not loaded it's not in my memory. It's in the Google Earth Engine. So I process all the thing in the Google Earth Engine and I exported only the output as a CSV file. And now I have the real output here in my memory. So just like a CSV file. So I have all the values for the samples. And basically I have for each spectral band, I have one column and I can access it right now.
If you had like a million points, and if you had to overlay like thousands of rasters, that could be computational, right? And
yes.
And
yes,
will Google block you maybe if you send too big number? I mean, how does it work?
To work with this number of points, my suggestion is don't use this function. Only export the output to Google Drive. So basically, if you look in this function, this is a exportation task. So basically, you can send like the name of the samples, the name of feature collection stored in Google Earth Engine. You can send it to the platform and export it to Google Drive. So basically, you just need to wait the exportation. Sometimes will take more than 1 hour, maybe 10 hours, but you will have the result in Google Drive, and after that you can download it. So basically, now we will filter this data frame to use only the bands that we are interested in. So we will have the land cover, the predicted variable, and the all the spectral values that was extracted, and I will convert it to factor to run in MLR3, and basically I will run my hyperparameter tuning using MLR3. There are several options to implement it. I won't talk about too much MLR3, and you can find more information in this link. But what I will do now is I will run the optimization and explain the code. So basically, now I have all the samples here in my machine loaded in R, and I will create a classification tasks. It is a basic object in MLR3. So I'm sending to the MLR3 my classification matrix and what is the variable that I'm interested in. So my target variable. Here I'm using random forest. So it's important to use random forest because after this hyperparameter optimization, I will classify the entire scene using Google Earth Engine. So I need to have the same algorithms and the same parameters implemented in Google Earth Engine because I don't have the Landsat data in my local notebook. So I'm only running a hyperparameter optimization here. And
but your model is fitted in R, and Google Earth Engine, it doesn't have an R engine. So how do you export the model to Google Earth Engine?
no, it's not possible. I need to retrain it in Google Earth Engine. Basically,
Okay.
what I will have here is the best hyperparameters for classify random forest for this specific area.
Yes, and the Google Earth Engine doesn't have this functionality of MLR3 to do the fine tuning, right? So you do the
No.
only fine tuning locally, then you get this fine tuned like a 1 or 2 parameters, and then you use that in the Google Earth Engine. That's what you're
Yes.
saying. Okay.
Exactly. And so in Google Earth Engine, I can only choose 3 hyperparameters: minimal leaf population, number of trees, and variable per split if I consider random forest. So basically what I'm doing here is finding the best hyperparameters in MLR3 to apply it in Google Earth Engine, retrain my algorithm, and classify the whole area. I defined this design. So here we will have all the available parameters that will be tested in MLR3. So basically, we can, I think it's more than 2,200 parameters, and I will show it when the optimization finished. And I created this tuning instance to define how it will work. So basically, what happens here is the tuning will considering 5-fold cross-validation to maximize the overall accuracy, and will test all the values that I established here in this design. So if I look it, I have all the possibilities of the parameters of hyperparameters here, and this function will test all and evaluate it by overall accuracy. And basically, after that, we need to create a tuner object and start the optimization approach. And the output is presented here. So we can see that we have 86% of overall accuracy considering all the classes, and we have these 3 values for the hyperparameters. And now,
okay,
we can
M-try1, it's a bit of a problem. It's too small.
Yes, but basically it's compensated by, for example, the number of trees. Because what happened here, he tested all the combinations, and the best overall accuracy was obtained with that. Of course, this could be, for example, this could happen because we have fewer samples. So here we have almost 400 samples. Probably if you have more samples, it will have different results. But we can visually compare it with, for example, a default parameter in Google Earth Engine, and we can see if it really produces a better result.
Okay, continue, please.
So basically, another possibility here is we can see, this is an important feature, functionality that doesn't exist in Google Earth Engine. We can see that what is the best Landsat metrics that are contributing to the classification approach. So the best metric is the SWOR2 percentile 75. So we can see this rank for all the variables. And here we have the 3 optimized values. So basically now we are ready to run the classification in Google Earth Engine. And what I will do is I will overlay again the points because it needs to run in Google Earth Engine. So if you check, this is a function that overlay inside Google Earth Engine without export it. If you check it, it's just a descriptor. The whole thing will be processed only when I show something in the map or only when I call a get info function. So in this case, it will only run on the fly when we see the result in the RStudio, in the map. So basically, I will create two random forest models. So one using 103 and the default parameters, and other using the MLR3 optimized hyperparameters. And I will train these two models. Again, this is only a descriptor. The whole thing will be processed when I put this result in the map. So I'm creating a training order to classify to create a model. And after that, I will classify the same images using two different models, and I will put all these layers inside Google, inside the map, to analyze and to see the result. So I like this visualization here. It's better. So now all the processing here is running on the fly. So basically, we have two classifications that were trained and predicted in this Landsat dataset, and we can visually compare the results. So this is the MLR3 optimized hyperparameters, and this is the default classification with the default hyperparameters of Google Earth Engine. And basically, and we can compare it to the real data using the Landsat median image. So basically, we can zoom in some part, and we can check if the result is, what is the difference between the results. So basically, we can see more, in some places, we can see that they are more consistent, but again, this is only a toy example. You need to create some different analysis. Probably some parts we lost some water, but we have a good convergence, a good spatial consistency, considering, for example, even high resolution data like this, for example. So we are seeing the result, and now we can export it. So we have a classification object, and we can export it to Google Drive, and we can start an exportation test. It's possible to export the Landsat median image, so we can export it to Google Drive too. And you specify, for example, some less bands than, for example, all the bands that were calculated. And if we check in the code editor, basically, I will reload here, all the exportation tasks that were started in we can see here. So it's basically running on the Google Earth Engine, and I will get the result in the Google Drive. So I download the data, so you can access the final results in this folder too. And it's possible to visualize it in QGIS. So yes, this is my code demonstration. And to summarize, you can try yourself these two possibilities of analysis. So, for example, you can expand the feature space using more percentile order reducers, and you can use Sentinel-2 data in the same area with the same samples to get, for example, a different map using better data. So to summarize the things, all the points, the use of Google Earth Engine by scientific community is increasing. So basically, in the last years, we have several publications in peer-reviewed journals that are using Google Earth Engine in different study areas. And we have some special issues in peer-reviewed journals too. And in my opinion, Google Earth Engine is an outstanding platform that allows users to test large-scale geospatial analysis quickly and on the fly. And for me, the best way to analyze, to run it, to use Google Earth Engine in your workflow is exporting a final result or intermediate result, as we did here. And you can export raw images, for example, like for all the Landsat images for 1 year, but it's not recommended and it will take too much time. And you can use multiple Google accounts to operate together and write in a shared bucket hosted in Google Cloud Storage. So it's an example of that. It's, for example, a land cover classification for the whole country or the whole continent. You can have several accounts sending a classification request to write in the same bucket. And it's possible to use Google Earth Engine to serve images as WebGIS application. And you can try to join to Geo for Good Summit. It's like an annual summit for Google Earth Engine users. And they launch, for example, the new functionalities in this event. So it's a good event to understand better the platform and what will be the news. And sorry to be a little hushed, but my goal was present end-to-end analysis and an example to integrate Google Earth Engine with R. All the code is available. I can respond some emails too if you have other questions later. And now we have time for the questions. Thank you.
Okay, thank you. Okay, we do have time for questions. So I think that was a very good demo. Giuseppe, we'll start. Please tell the question, I'll repeat, yeah. For classification, you mean? Okay, so in Google Earth Engine, can you use random forest for regression problems?
Yes, you have several models available in Google Earth Engine, and you can specify if you run it for regression or for a classification. So this, you can see here all the, in the classifier, you can see all the available models, but you can specify if it will be a regression. I think it's in the output. So you could specify if it is a classification problem, a regression problem, or a probability. For example, for binary classifications, you have the possibility to export the probability of each class.
So even though function is called classifier, it actually can be used for regression problems too. So it's a bit hidden.
Yeah, it's misleading, but yes, it's possible.
And, yes, it's a pity that because you do in MLR, you already do the work, right? You do this optimization, and that you cannot then use exactly that model you got from MLR, that you cannot deploy it in Google Earth Engine. And that's because, yeah, I don't know, is there any intention to make Google Earth Engine, compatible to more, more open source solutions, or?
No, that's really a good question, because actually we can't extend Google Earth Engine. So for example, we can implement some native function here. We only can use it. So the decisions are totally dependent from Google team. So basically, I use Google Earth Engine for a few years, but the whole concept here, it's not like a deploy a model, but run the whole thing again. So for example, even if I had the my model trained and I save it, I can't put it in Google Earth Engine to run, for example, for other area. I need to retrain the model and export only the output. So all the things need to run on end-to-end again. But I know that for deep learning approaches, they have some type of cloud solution named ML Cloud, I think, that you can host, for example, a deep learning, a neural network trained in TensorFlow in there. And after that, you can call it from Google Earth Engine. But I think it's just for neural network. For other classical machine learning approaches, I don't see anything.
Okay, and there was a question somebody asking Q&A. Somebody asked about the bottleneck. So, like, let's say if you have more points or something, then slowly your Google Drive, I think it's on the free account, it's something like 30 gigabyte or something. So then your Google Drive runs out of space, and then you will experience the storage problems, right?
Yes, actually, if you really want to use Google Earth Engine for huge analysis and generate big images, you need to, the best option is use Google Cloud Storage, that you will have more option, but you can expand your Google Drive account too, but for more production, to produce a big Earth observation result, you need to run some type of the cloud solution. And something I didn't mention, so here you have as personal asset, so this is your asset code. So you have for free this amount of gigabytes available. So for example, any analysis that I want to only access in Google Earth Engine, I can rewrite it in Google Earth Engine. So basically, for example, if I don't need the output in my local machine, I can rewrite the output in the Google Earth Engine to access it in a more quickly way as, like, for example, a regular Landsat image. But in general, you want to recover the data and export it from Google Earth Engine to work in other platforms. But it's a good option, for example, to split parts of your process. You can process, for example, some NDVI calculation and generate the median as asset, and after that you can train using the output of the first analysis.
And so, like, Microsoft has the cloud services for like R, to compute in R, to deploy R. And if does Google have something like that you deploy like a R, and maybe then you could connect Google Earth Engine and you know, some R installation? Do you think something like this could work?
Yeah, I didn't see anything like it, but probably.
Yes, just a second, Ezra, think he can help here.
One option there is that if you run a server in Google Cloud, and if you run GDAL on that, and you encrypt GDAL with the Earth Engine driver, and you can directly read tiles from the Earth Engine archive. So you can do your own processing on your own rented servers, reading from the Earth Engine archive. That's all processing is an outside Earth Engine. You don't use Earth Engine processes, but you use the data that's there. GDAL has an Earth Engine driver.
Did you hear that? Did you get that, Leandro?
Sorry, only the last part, that GDAL has a Earth Engine driver. It's right.
Yes. So the idea is that you use the Google Earth Engine functionality in the cloud installation.
You don't need to do Earth Engine functionality. You have access to the data.
Okay. So from Google Cloud, you can access the raw satellite images. And so basically you still do computing inside Google infrastructure, but you don't use the Google Earth Engine. Yes. but you use the data from the Google Earth Engine. So that could be a solution, like the backend solution to compute your own way with the Google Earth Engine data. Okay, no, okay, good. That's good to know. Okay, are there any more questions? Giuseppe? Did you hear that? That you can mount the Google Drive?
No, I couldn't hear, sorry.
Okay, I will repeat. So Giuseppe said that you can mount the Google Drive inside inside your server, and then if you run out of space, so you can move the data so you never run out of space. You continuously move the data, so you always keep it within the limit of 350 gig or something. So
Yes,
that's
yes.
a trick.
So
that could be a trick. Yeah. How's it called? R clone, yeah, with the R clone.
Yes, you can export the result, download it, and erase. So you can use Google Drive only as a temporary storage to get the outputs from Google Earth Engine. So it could work, and this package it's really easy to implement that because RGAA provide access to Google Drive using an API, the official API. So it's could be a good way to implement it.
Okay. More questions? Yes, in the back. Please speak loudly. Okay. So there's a EE_S_raster function to export the image and get it locally, right? And that's in the RGE package. Yeah, okay. Okay, so there is already some wrapper to get the images, but then you depend on your bandwidth and
yes, and probably
to download, you know, the whole world at 30 meters. Yeah. Just a little chunk. Okay, more questions? So you mentioned also this visualization. So once you make the analysis, you know you've been using the leaflet, but you know it's useful to create kind of like a web mapping app. So you put some HTML or something somewhere, and then people can access it without needing to run the code and or you know use R. So tell us something about that. How complicated is that? How much coding do you still have to do, and is that something that you can do then from R, or you have to use some Google Earth Engine?
So actually, to integrate Google Earth Engine with any type of WebGIS solution, you need to create like an access token to get the result for any specific analysis. So for example, for the result of annual NDVI or for specific Landsat data, but you need to refresh this token, for example, every day. So I did that. So you need to create like a publication link through the Python API and have access to a URL and to a token that you provide to you, like a tile service to access that analysis, and you can put it in any type of application, like a leaflet application or open layers application. But you need to handle this token. So a good way to do that is republish all day and refresh that token. So I think I put here in the there is a application named TD Lights. I didn't remember, but these applications show how integrate Google Earth Engine with any type of web applications. So yes, this one. So mostly you need to publish the layer using Python, and you can access the result trendy light. So this one. So you can access the output of this analysis through a tile service API. That is provided by Earth Engine. But it's not easy, but it's possible.
Okay. Yeah, we have on Thursday we have a team talking about the map view. So you go in like few lines of code, you create a web map, you know, you customize it and you set up things. So that will be useful to make also for Google Earth Engine to like quickly create these web mapping apps. But you said you need a token, and yeah, it's all a bit more complicated. Yeah, there.
Yeah, but yeah, thinking better now, I think other possibilities, like for example here, I'm using the RGAA package, so I only create this map representation that's probably is using map view, so you can integrate it with the R ecosystem, because all the token creation and all the steps that I described probably is implemented in this function add layer that is implemented by RGAA. So probably could be an option using this output of this function here. So this is a map view instance to extend the visualizations in the R.